All right, let's go ahead and talk about section 4.2. So this is where we're going to be using some algebra to evaluate these limits. So some of you already know, or you might have guessed, that there might have been an easier way to evaluate, especially when we were looking at the table. And that's where if you plugged in the x value, if you got an answer, then that would be the limit. So that's going to be our goal with these, is to see if we can plug in the value. If we can, plug it in, and what would be your answer. So like for A, you're going to plug the 2 in for x, and work it out, and it comes out as -2, so that's your limit value. For part B, you can plug in the -3 and for all of those x's, and you end up with 9 plus 3 plus 3, which is equal to 18. Wait, no, it's not. 15. For C, plug in the 2 for the theta, so we end up with sine of pi over 2. So that's 1. For D, plug in the pi over 4 for the theta. End up with tangent of pi over 4. So that's going to equal 1 as well. So if you can keep doing that for all of them, that's your goal. So like if we plugged in 0 for that x, we end up with 5. Oh, now this one, there's no x to replace. It's just a constant 9. So if there's no x to replace, it just stays as 9 no matter what you do. For G, plug in the 4. So you end up with ln of the absolute value of -1. So ln of 1, which always is 0. And then for this last one, plug in the 1. So ln of 1 minus e to the first all over e to the 0. So 0 minus e over 1 gives you -e. So not too bad. So limits, they've got all of these properties here, which most of them are kind of common sense. So like the limit of a constant is a constant. This one, you can, if there's a constant being multiplied to everything, you can factor the constant out. For the rest of them, if there's an arithmetic operation in between them, you can kind of do the limit of each thing separately, especially term by term. This one's going to come up quite a bit on number 5. So let's go ahead and try some more examples that are a little bit trickier, because sometimes you can't actually plug in the value because it gives you a 0 in the denominator or something bad. So in those cases, you still want to try to plug that in, but eventually. So you have to manipulate that function, which usually requires like factoring or maybe using a trig identity or something like that to work this down so you can actually plug in this value. So like for part A, we're trying to plug in the -5, but we can't right away because that would make the denominator 0. So if we factored it, that would give us x plus 5 times x minus 5, which you can now cancel. And get 1 over x minus 5. And so now you can plug in your value of -5 and make it -1 over 10. Okay, for part B, same thing. You can't plug in the value of 2 because that gives you a 0 in the denominator. So you have to factor stuff. So that means you got to remember how to factor x to the third. So it's been a while since you factored one of those, but you got to remember how to factor them. So x to the third minus 8 factors into x minus 2 times x squared plus 2x plus 4. And then the denominator, x minus 2, x plus 2. So your x minus 2's are gone. And we have x squared plus 2x plus 4 all over x plus 2. And now you can plug the 2 in there. So 4 plus 4 plus 4 all over 4. So if you add those up, divide by 4, you end up with 3. So that's kind of the name of the game for all of them. So for C, we're going to want to factor this one too, but we got to factor it by grouping. So we'll group the first two terms together, so pull off your x squared. Second two terms, pull off a 4. And then we're going to group the denominator as well. So in the first two terms, pull off x to the third. And in the back two terms, the only thing you can pull off of those is a 1. So now we have your x minus 3 that's common on the top, so pull it all the way out. And x minus 3 is also common on the bottom, so pull it out. And now your x minus 3's cancel. And you have x squared plus 4 on the top, and x to the third plus 1 on the bottom. And now you can plug in the 3. So 9 plus 4 on top, and then 27 plus 1 is underneath, which gives you 13 over 28. All right, part D. This one we're not going to factor, but I'm going to use a trig identity. So sine squared, I can change that around into 1 minus cosine squared. And I'll leave the rest of it alone. And now I can factor the 1 minus cosine squared of theta. So 1 minus cosine times 1 plus cosine times cosine over 1 minus cosine. So your 1 minus cosines are gone, and we have 1 plus cosine of theta times cosine of theta, and now you can plug in the 0. And cosine of 0 is 1, so we have 1 plus 1 times 1, which usually comes out as 2. All right, I'll let you do E. You can look in the notes for that one, and that one's just more factoring. But example F, let's talk about that one. So again, you can't plug in the 4 because that makes a 0 in the denominator. But we can factor it, or at least factor the top. And it doesn't look like you can, but we really can, because we have really a square minus a square. And the x, like, well, that's not really a square. Well, it kind of is, because it's really like a root x squared. So you can factor into root x minus 2 and root x plus 2, which will cancel out the denominator. And it's left with just root x plus 2, and now you can plug in the 4 to give you 4 as a result. So a lot of these are going to involve some sort of a factoring technique. So if you need to brush up on your factoring, brush up on your factoring. Okay, I'll stop the video here, and then the next one we'll look at some other types.